Okay, now this one is going to be on the graph module and the marker module. I have each of these marked as IXIs. They're IOTA extension interfaces. They process transactions that come on the IOTA Tangle and deal with them in this manner. So we're going to talk first about graph IXI and what it is. Graph IXI is a module that allows you to make arbitrary graphs. So an arbitrary graph has a vertex which has some data associated with it and any number of edges. And one of the things that you could do with that is, so that gives you initially a directed acyclic graph, but you could publish many vertices to a single data, and that would allow you to create a compound vertex from which you can have cyclical graphs. At least effectively cyclical graphs from the perspective of the data. For the purposes of cubic, we keep it to acyclic graphs. So let's look here. We have the graph IXI, and hopefully this is going to get clear right here. The vertex is marked by this circle, and it contains these edges and this data. The first vertex is going to have a list of up to 27 edges. It will have in the extra data digest portion, the hash of the bundle fragment of the data that it's interested in looking at, and the address might be it could be anything, whatever the user wants to put into that address. That could be an extension of a tag, and then it could have a tag to help notify you about some metadata properties of this vertex, so that you have some vertices that are a little bit more searchable, aside from vertex structure itself. You'd have any number here. You could have, for example, you could even have the issuance portion of this equal to the number of edges, or rather E sub n, or that's the the number of edges, I guess, yeah. And if you have that, then you could already know ahead of time how many transactions it's going to be before you find your last edge. And this is once it's been serialized into an IOTA transaction, because these are not these are actually in the signature portion or message portion. These are not index values, and they shouldn't be expected to be searchable. So what actually happens is the graph IXI should take these all out and reflect them into its own virtual subtangle, such that it has some head which points to the data over here, and E1, or yeah, we'll just say E1, and that's all that edge would contain. It wouldn't contain anything else necessarily, and the next one would point to that and have E2, and so on until we get to the head, where when we create the head of our reflected one, it would point actually to this transaction, this serialized vertex, where each of these would not necessarily point to the true E1, but reflected E1. So I'll change this to, rather than E, I'll change it to reflected. And then that way, when we want to go back and parse this, we just traverse down to the bottom. If we were building it first, we'd traverse down to the bottom. We'd make this reference our first one, and so on until we get to the top when we want to serialize it, if it's not already been serialized, and we were creating one, then we would traverse down to the very bottom, start at R1, and move on up until we get to our last edge, and have everything created, or perhaps we do this in reverse order. We do R N. We could do that. Doesn't really. It could be either way. Implementation might and -1 and so on until we get to NR0, and then our true head would be. It would look at the serialized vertex transaction as the hash of this. That way we could go down, start at R1, we could start building this message, and so on. We'd know by a modulo 27 how many is going to be in the last vertex we're interested in. So this is an implementation detail. This part is what's most important for what gets transmitted over the tangle. This is how we reason about the data locally, in other words, and this is how we communicate about data globally. Next, we'll look at the marker extension or marker module. The point of a marker module is so that you can have a Merkle signature scheme, or it could really be some alternative signature scheme aside from a Merkle signature scheme, whatever's necessary for you and your particular use case. But I presume a Merkle signature scheme, because those are, I think, highly secure, and they can be done in a multi-tree fashion, such that you can have very long-lasting signatures. And this Marker IXI, we're going to be able to mark, hence the name, we would be able to mark a specific transaction and pin that by that signature so we're signing a transaction rather than something else. Or the transaction that we are pinning there is actually part of what we're interested in. So this Marker IXI is going to, for example, say we have a vertex and we want to sign that vertex. We don't want the vertex to be able to move somewhere else by someone taking the vertex and replaying it somewhere else or reorganizing it on the tangle somewhere. We just want to be able to take that vertex and sign it. And this is how we do it. So this data down at the bottom, I hope this is legible. Yeah, it looks minimally legible. This data down at the bottom, right there, would be this first transaction V, some thing. And so this last one that would be pointing to it would be that BN, the last branch. So the very top here is going to be our signature. This is the part where we use the native IOTA signature scheme, just a one-time signature. So S1 is the first of those signatures, where we presume that it is a possibly multi-signature implementation, and that's going to be for some added security. The first signature only signs the first third of the bundle hash, and so on. And to make sure that, so we do this so that we can use the normal IOTA transaction validation scheme to validate this signature if we want. And therefore we put the value equals minus height, where height is the number of things here. So I'll actually rename this to minus b sub n. And here I'll rename this to b sub n. So this, where the address is the same on both of these, it's just the public key associated with this one-time signature. this is going to create an overall net zero change in the bundle of that given address. So it's not going to need to check any ledger for validity. It's only going to need to check that bundle for validity, and there's nothing in the ledger that we have concern about. We include this HTB1, so this B1 right here, the hash of this we're going to put in the extra data digest of signature 1. We do that in signature 1 just because that's signature 1 is where we begin validation, and well, it could really be anywhere, but we might as well put it in there. We could put it anywhere else, but it needs to sign at least B1 so that we know that we're also signing the Merkle branch that we're concerned about, and we're pinning that. So that gets included in this extra data digest, and we can create the whole bundle essence prior to publishing any of these, and we know what the bundle essence is after we've attached B1 to the tangle, and then we compute the rest of the bundle hash, and we begin to attach each of these on top of that. Obviously, none of the bundle essence can change after we've published B1, and well, after we've published B1 and created the essence with HTB1, which is the hash of this, or the identifier or pointer to that. We're going to create the signatures and attach them to these transactions, and we'll publish these to the tangle, and that will pin B1 such that if this gets reorganized anywhere else on the graph, it will be invalid, and therefore only this is valid. Only this instance is a valid signature by the public key identified here. E equals the signature parent proof, or rather, let's see here, yeah, and I equals the signature root distance. And then we could put, for example, we could put something else down in BN, but the point of this is right here. This creates another little virtual graph so that I can go back and look back in time to see that the Merkle root here, which I don't need to declare, I can just see, I can generate it, so I don't need to declare it. It's implicit. I can go through here, generate my Merkle root, and then here I could go and check often. That'll have to be another portion of this. I can go check on a different bundle a signature proof of that this Merkle root was signed by some parent Merkle root, and then this I is going to be the signature root distance, or the distance if I'm at this tree, because these Merkle signature schemes are trees. Oh, this one was not a binary tree, that's my mistake. I'll just draw it out like that, so that'd be a binary tree of 8, or 4 rather. If I start with that tree, and I would go back, and how many back would I need to go before I get to the root? So if I'm on my first one, that would be 0, 0 if I'm on, and then it just increments from there. And then obviously, and then also, if I was doing this back on previous ones, I'd also go back previously to the other ones that have been pinned. And it would be okay for those ones to be reattached, because those are for the purpose of proving that that some Merkle public key is indeed the descendant of a different Merkle public key. And then the data. So to put it into a final set of transactions, we'd have first signature through the nth signature, the hash of the branch beginning that we're pinning, the number of hashes in those branches. That would actually be, that's my mistake, that would be B1 through B27. Can I fit that in there? 1.27. My bad. And then the address would be the public key of this one-time signature. This one, the value would have to be 0. And this signature would just carry on. Then down here, the signature parent proof, I neglected putting that I in there, but I have it listed out here what would be in this first one, and then the rest would essentially just omit that, because from the height we'll know by modulo how many transactions we have to go down to find the final proof. And this is how we would mark a subtangle as pinned and signed by a transaction issuer. I'll erase that after the video.